Okay, this is the last section.
Righty then.
We may not run over too much today. So we're going to talk about resonant or tuned circuits. So you're going to see some more math.
Okay.
We're going to talk about impedance and reactance. They're very important things. So impedance is opposition to alternating current flow. We also measure it in ohms. And that's different than resistance. Remember, resistance doesn't care about frequency. Impedance does.
Say that again.
Resistance doesn't care about frequency.
Right, okay. Yep.
Impedance does care about frequency. We'll find out that capacitors have a high impedance at low frequencies, and it becomes lower and lower at high frequencies. So a capacitor at DC looks like an open circuit. It won't conduct any current. At extremely high frequencies, it looks like a short circuit. So its behavior is in between, whereas an inductor at DC looks like a short. It's just a piece of wire, and it doesn't create much of a magnetic field. Okay, at DC, it's a constant field. But at high frequencies, an inductor has a very high impedance, and it becomes essentially an open circuit for very high frequencies. So those two operate just the opposite of one another. But it turns out if we put them together, okay, we can find a point where the opposition, or what we call the reactance when we talk about the specific ones, is equal and opposite, and it cancels out. And that's a point we call resonance, where the it looks like a pure resistance at that point. You don't have any of the impedance effects, and we'll talk more about that. So when we talk about the individual inductors and capacitors, we refer to their opposition as reactance, and we use the capital X to represent that, where we use the capital Z to represent impedance. And if you look at the formula, okay, impedance is composed of the resistance, in other words, the real value resistance, and the sum of the inductive and capacitive reactances. And because inductive reactance is positive, capacitive reactance is negative, okay, we add them together and we see the difference. Okay?
Okay.
Now you'll see this guy, little j.
Mm-hmm.
You familiar with little j?
No.
Little I?
No, mind blown today.
Okay. Well, I kind of doubted that you did. In mathematics, they use small I to represent imaginary numbers.
Right.
In electrical engineering, because we use small I to represent current, We use all J to represent imaginary numbers.
Okay.
Okay. And what that means is that J or I is how we represent the square root of -1.
Say that again. Square root of -1.
Yes,
That's what
it's
the J.
imaginary. Huh?
All right.
And it turns out reactances are on the imaginary plane. They're out of phase with the real current.
Okay.
You know, kind of like in the science fiction movies where all of a sudden something happens and people are on another plane and can't interact.
Yes.
That kind of stuff. Yeah.
Yep. Gotcha.
So the formula for inductive reactance is 2 times pi times the frequency times the amount of inductance. And that will give you a value in ohms at a specific frequency. For capacitive reactance, it's 1 over 2 times pi times the frequency times the capacitance. So it's kind of a reciprocal value. But when it turns out that the inductive and capacitive reactances are equal, okay, that's what we call resonance. And if you actually do the algebra to put these together, you can come up with the formula for resonance. So that resonant frequency is 1 over 2 times pi times the square root of the product of the inductance and capacitance.
Do I need to remember that?
You just have to remember the principle.
Okay.
Right, so when we have a resonant or tuned circuit, and we're looking at a parallel resonant circuit down here, the animated one.
Yeah.
And what you're seeing is energy being stored in the capacitor up to the point where it stops, current stops because it's charged the capacitor up. Now the capacitor starts to discharge and is supplying current through the inductor and building up a magnetic field. So we're converting the energy that is in this electric field and the capacitor, okay, it moves over to create an equivalent magnetic field, energy-wise, in the inductor. If there's no loss in the circuit, this would happen indefinitely, and that was what we call resonance. It would just sit there and oscillate, and the frequency of how fast that energy moves back and forth is from that formula I just showed you. 1 over this 2 pi times the square root of LC. So the important thing to remember, we can have a series or a parallel resonant circuit. In this case, it's a parallel one. I think next chart might have a series. If it's a series resonant circuit, it means that we'll have a very low impedance at the resonant frequency. It'll essentially be equal to whatever the resistance value is. If it's a parallel circuit, it's going to be a very high impedance at the resonant frequency. And this, again, here's the formula. So if you set X sub L equal to X sub C, you can manipulate, come out with 1 over 2 pi. You set these equal, okay. I didn't do the math here. But that's when the energy is going to be equal amount of energy transformed back and forth between the two. If we plot the reactance, so here we have on this impedance line, which would be ohms, we have a resistor. It's going to be a constant value. It doesn't change with frequency. If that was like 100 ohms, over here at infinite frequency, it's still 100 ohms. We have a capacitor that is down here. It's infinite ohms at zero frequency. And as the frequency increases, it goes to zero. The inductor is the opposite, where at zero frequency, or DC, it has 0 ohms of impedance or reactance and increases to infinity at infinite frequency. This is like the one we saw, a parallel resonant circuit. Over here is a series resonant circuit where the L and C are in series. Now, if you notice assume at DC, you're going to get no current flow through this capacitor, right? It's going to look like an open circuit. However, the inductor is going to look like a short circuit. So at DC, this is going to pass, as much current as is allowed. On the series circuit, it's not going to pass any current at DC because of the capacitor. So it doesn't matter what the inductor does. As we increase the frequency and the capacitor starts to pass current, the inductor will start to block current. And when they're at resonant, they sort of cancel each other out. So all we see in the circuit at resonance is going to be that series resistor. Likewise, over here in the parallel circuit, as we increase frequency, the capacitor is going to start to conduct, the inductor is going to start to block, and at resonance, they cancel each other out. So all we have in the circuit is whatever value R is. Ready to move?
Yep.
Okay, so this just again is showing the minimum impedance at resonant frequency if it's a series circuit, and maximum impedance at resonance if it's a parallel circuit. Those are the key points to remember. Here's some plots for a series resonant circuit. If we plot impedance versus frequency, you can see that it starts off very high impedance. When you get down to the resonant point, it's very low. And then as you go up in frequency, it goes back up to a higher impedance. The second one is plotting the current. So at a very low frequency, we have very low of, if any, current. And the current increases kind of exponentially until we get to resonance. And resonance is going to be at its maximum, and then it's going to decrease as we increase frequency. We do the same thing for parallel, except here we start off with a low impedance, and it increases up to resonance, and then decreases. And it starts off with a high current at low frequency and low current at resonant frequency and then back to a high current. So because these parallel and serial operate as opposites, we make use of those in electric circuits depending on what we're trying to do. Whether we need something to be passing current at a resonant frequency or blocking current at a resonant frequency. So which of the following is a resonant or tuned circuit?
This is probably the one I'm going to fail. Alpha.
Very good. Which of the following is combined with an inductor to make a resonant circuit?
I don't know. Okay.
LC circuits are just that, LC, inductor and capacitor. So any inductor and capacitor, either in series or parallel, will have a resonant frequency at some point, depending on their values. And sometimes we don't want those resonant points and have to do things to fix it. Okay, back to switches, which open and close circuits. And we talked about the single pole, single throw. Now we're going to talk about a single pole dual throw or double throw, where we can connect a single circuit between two other circuits. And in this little diagram down here, we're either connecting this 15-volt battery to this electric lamp or to this LED with the current limiting resistor.
Oh, okay.
So the switch is going to turn this on or this on. We showed this before, all the different types of switches, or some of the other types of switches. There's lots of variations. What is the function of a single pole double throw switch?
Charlie.
Okay, I mentioned relays. Relay is an electrically controlled mechanical switch, which is why it's different than a transistor switch. They're both electrically controlled. So one's a mechanical switch and one's an electronic switch. So in the case of the relay, we have what we call a solenoid, where you have some windings around some form of iron, and that creates a magnetic field which moves this lever between the two poles. So it either opens or closes the circuit depending on how it's configured. So in this case, if we close switch 1, it should light up the yellow LED. Because it's going to connect this 5-volt battery up to the normally, actually these are labeled wrong. It should be normally open to the LED. I didn't draw it, so it's not my fault. What is a relay?
Alpha.
Meters. Meters display electrical quantities as a numeric value. They can be analog or digital. You see them on the output, displaying output voltage on a power supply, output power on a transmitter, all sorts of devices may have a numerical display. Your cell phone has a numerical display. Here's some more old-fashioned analog type meters. Still around, but most of the newer stuff has electronic digital versions of them. These are some of the digital panel meters you might have seen. So which of the following displays an electrical quantity as a numeric value?
Charlie.
Integrated circuits. Now that we have diodes and transistors and these little capacitors and inductors, resistors, we can put millions of those things together on a single little slab of silicon and connect leads to it and package it and call that an integrated circuit, where it has all these interconnected components. It could be a microprocessor, processor in your computer, something as simple as a voltage regulator. They come in all sizes and shapes. And all it means is it's a lot of circuits integrated together in a single package. This is what one of them looks like with the cover removed. And you can see this black square is a piece of silicon, and all those little looks like houses and farms and all those things.
Yeah.
Are transistor arrays and memory and all sorts of things. And you see the shiny things, those are all gold wires that connect to various points and then connect out to these external leads.
Why do they use gold?
Because gold doesn't corrode. Even though these are supposed to be hermetically sealed.
No, I see.
So if you would go collect a truckload of these things, you could melt them down and get some gold. This is a voltage regulator, which is also an integrated circuit, because in it, it has a number of components. It's got a transistor, maybe more than one. It's got a little comparator circuit, which we have a lot of transistors to make it. It has a voltage reference, which could very well be a Zener diode. It has some resistors, all in that little package. So what's the name of a device that combines several semiconductors and other components into a single package?
Charlie.
What type of circuit controls the amount of voltage from a power supply?
Alpha regulator.
Right. Fuses. Fuses are designed to open a circuit when a certain amount of current flows through it. And they're rated in, like half an amp, 1 amp, 2, 10, whatever. Lots of different values. There's even pico fuses that you can have inside circuits, which operate at very low currents when you're trying to protect some very delicate electronics. But its main purpose is to prevent damage by whatever's connected downstream, and to prevent possibly fire.
Mm-hmm.
Because if you didn't open the circuit,
Overheat and blow up.
you could overheat something and create a fire. Here's some typical fuses. You see these blade fuses in automobiles nowadays, in some electronic equipment. These are more of the old-fashioned, like wired. You also see them without the wires as cartridge fuses, like this one, which snap in a holder.
Mm-hmm.
Lots of different kinds. They all do the same thing, just different values. So what electrical component is used to protect other circuit components from current overloads?
Alpha, the fuse.
That was a really hard one, wasn't it?
Yeah, I couldn't handle that.
Shielded cable.
Mm-hmm.
We use shielding in cable to prevent unwanted signals from being coupled into the wires. Because if you have an RF signal and it has an electric magnetic field, when it intersects a wire, it can cause current to flow in that wire, which is not a signal you want. So one way to do it is with a shielded cable, and it's basically a Faraday cage.
Gotcha.
Named after Michael Faraday.
Mm-hmm.
So the way a Faraday cage works, I don't know if you have one of these credit card protectors. It's a metal like wallet that you put your credit card.
RFID wallets and all that.
Right. That's a Faraday cage, basically. So you have free electrons running around in this metal cage, and when an electric field comes by, it causes those free electrons to kind of shift to one spot, and you see absolutely no electric field inside this Faraday cage. But it looks like the electric field passes through. In other words, you sort of see it coming in this side, you see it exited over here, but it did it via recombining the free electrons,
Mm-hmm.
and nothing happened inside.
Now, are all Faraday cages made with copper?
No.
Okay.
Could be aluminum. It needs to be a conductor, a fairly good conductor. And they don't necessarily have to be solid. It depends on the wavelength of the field. So if it's low frequency, which has very long wavelength, you can have very big holes in it, as long as the holes are smaller than a wavelength. And then we talk about wavelengths probably next week.
Okay.
You could wrap your credit cards up in aluminum foil. That'd be a Faraday cage. Or
my sister has a wallet.
You can get plastic bags that have a metallic coating on the inside.
Mm-hmm.
That's a Faraday shield.
Oh, wow. Okay.
Put your cell phone in it, and supposedly people can't contact you, but
I haven't tried one yet.
Okay, which of the following is a reason?
I know of a school where they when the kids come to school, they're given a bag, and they
Right.
stick it in their lockers, so they can't be tempted.
Yeah, I'm kind of lax with my homeschool kids.
Yeah,
and they always have their phones out, but they're paying attention and they're actually taking pictures of the charts and stuff.
Mm-hmm.
So as long as they're getting the answers right, I don't care.
Yeah, I gotcha. Anyway, this would be Charlie.
Okay, so what did we learn about resonant circuits? That a series circuit has a very low impedance at resonance. Parallel has a very high impedance at resonance. We learned about single pole double throw switches that can switch between two different circuits.
Mhm.
Uh, Relays are electrically controlled mechanical switches. Meters display numeric value, either analog or
Digital. Yeah.
digital. Integrated circuits are just a collection of analog or digital smaller devices all in a single package. A voltage regulator maintains a constant voltage on its output from a higher voltage on its input. Fuses are used to protect other components and prevent fires and hopefully other damage, but a lot of times by the time the fuse blows, uh, you've prevented a fire, but you probably lost something that has to be replaced. And
Yeah.
shielded cable is used to prevent coupling of unwanted signals or the reverse, the broadcast of unwanted of signals. Is a uh, electromagnetic waves running through copper wire or any kind of wire can radiate. So if it's inside of, say, a radio, you don't want it radiating to other stuff. So you tend to use shielded cables to connect things together.
Yeah. Otherwise, you get interference and stuff. You can't get your
Right.
signal in.
So
Where were we supposed to go to get like